Any questions from the last sections that we had? As we had 11.1 and 11.2, they were all dealing with functions and going through and adding, subtracting, multiplying, dividing those in 11.2. And then we were in 11.1, that's what we did in 11.1. 11.2, we were putting them inside of each other and coming up with their solutions. Anything there we need to go through? A square root one. You mean something like putting like a f? Okay, let me grab a pen here so that we can do that. It's not dark enough. And what was that again? You had f of x, 2x minus 8, yep. Square root of 2 minus x. Okay, and what are we doing to it? Are we adding it, subtracting it, multiplying it? Okay, now the only thing we can do if we multiply this is just simply multiply it by this piece by each piece. You can't really work it out. So all you can come up with is 2x, the square root of 2 minus x, minus 8, the square root of 2 minus x. That's all you can do to it. Can't do anything else to it. It's the max of what we can do to it. The domain, okay. Now the domain is limited because this is a square root. And under square roots, we can never have anything negative because we get imaginary numbers if we do. So if I take just this piece, 2 minus x, and set it greater than or equal to 0, and I minus 2, then divide by -1. And as soon as I divide by that -1, this piece is going to make that flip because of dividing by a negative. So I really end up with x needs to be anything less than 2. So my domain on this one would be negative infinity to 2. Okay, does that help? Okay, now the other things you got to watch with domains is if it's got a denominator, because the denominator can never be 0. So if you had something like g of x is equal to 2 over x plus 4, and f of x is equal to 2x plus 1, and you were going to put these together, your domain, you would have to watch because that could never be a -4. So if you set x plus 4 equal to 0, what this means is x could never ever equal a -4. Okay? And so that's the piece you'd have to watch. And then debating it, depending on what you're doing, if you're adding these, you just put them together and so forth. Okay? Yep. But there isn't a whole lot with square roots that you can really do with them outside of just multiplying them and leave them alone. Okay? Yep. All right. Anything else that we need to go over? And this, for some reason, is not holding and showing everything that I've got up here. Oh, that's why. We'll get it so it works. First part of this tape might be just a mess, but that's a little bit better. Okay. Anything else that we need to take a look at with that? Are we good? Okay. So let's continue on, and let me get this to focus a little better, maybe. I hope it does. There, that's better. Okay. So let's go into 11.3. And 11.3 looks like it's kind of nasty, but it really isn't. It's story problems. But all of the story problems that are in here are basically formulas. And they're formulas that deal with exponential formats. And when we work with exponential stuff, it ends up giving us a different shape of graph. So far on our graphs that we've had straight lines. So we know all about those. And we've had those for quite a while. We had graphs that did this, and they were in our rational pieces. And we had graphs that came up like this and went like that. That was a cubed graph. We've had graphs that are parabola based, and those were our quadratics that we happen to have. And in our last chapter, our graphs are going to look a little bit different here too, because they're going to approach x and then just kind of go way up into the values that we have. So we've had all these different shapes and different formats of graphing in here. So what we're going to look at first is graphing exponential functions. And again, in your and with your graph, we can look at those on your graphing calculator. And so we'll do those there, and so you get an idea of what they look like if you did that. Applied problems, and again, these are exponential growth, exponential decay. So growth means we're getting better in our company. Decay means we are losing money if you're looking at it in a company. And compound interest. And so those are the three areas that we'll take a peek at. So in exponential functions, what in the world do they look like? Well, they are basically an exponent or a base raised to some form of an exponent. And we can raise that in whatever value. So here we need to know that b needs to be greater than 0. And if it were 0, what would happen? I'd have 0 to some power, which it is still end up being 0. So it wouldn't make a difference. And b cannot equal 1, because if it equals 1, what's going to happen there? 1 to the 5th power is still 1. 1 to the 9th power is still 1. 1 to the 275th power is still 1. And so we can end up using 1 in there. So these are the two things that we have to be careful with. And that x is any real number, meaning we're not going to have imaginary pieces at this point. Okay? So there won't be anything that's imaginary that we're going to work with. So then what happens with these? And again, this is just, and again, if you don't remember the stuff per se, that's okay, because it's not going to come back up. I'm more concerned that you know how to operate your the formulas that you happen to have. So b is greater than 1, and so we know that b to the x is greater than 0. b increases to the right. It's called the growth. And b to the 0 power is 1 as always, and the x-intercept where it's crossing is going to be at 0, 1. If it's a decrease, the right is called a decrease. So if x is decreasing, then we'll have that happening, but it's still going to cross at that point. So if we take a look at what a graph looks like with both of these, this one is a growth, exponential growth. This one is an exponential decline, because we read them from left to right. If you have a company, you want this to happen. You want your company to grow. Now, does it grow at that steep of a rate? Probably not, but it shows a growth that takes place. You do not want your company doing one of these, because that is not healthy, because what you're having happen with your company is it's decreasing in here and you're losing money. And so this is when companies start to find that they're going to be under foreclosure, or they're going to do bankruptcy and that type of stuff. So you don't want this type of thing happening. The horizontal asymptote is this line that's in here, and it's your x-axis that you happen to be looking at. And all it does is shows where that graph is rising or where it's declining within those. And so again, just put it in here so you had a picture, and you could see what is taking place with those and what we end up doing with those. So the first problem that we have, all of your story problems will have a formula in them. Okay, so they're all going to have some type of a formula. And again, these are examples, and we will go to your sheet in a minute. These are not in your sheet, so just hang on to that for a minute, and we will go back to that and see if we can set those things up and figure out what happens. Now, you will need your graphing calculator with these, because the exponential parts you are definitely not going to try to do in your head, because some of them are decimals, and a variety of stuff happens to those. So our story problem, it says a scientist has 10,000 bacteria present when T is 0. So basically what this means is that the Petri dish has just been filled with the bacteria. So we're going to see what takes place with that bacteria. And as you know, with bacteria, it always grows. It doesn't decline. And some bacteria grows very, 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 very rapidly, and it grows quite quickly with what you have. So she knows that the bacteria grows according to the function of y equals y subscript 0. Now the difference between these is this y is the starting amount of bacteria. This y is the finishing amount of bacteria. So after that certain length of time of what takes place, where T is measured in hours, how many bacteria will be present at the end of one day? So if we're going by hours, how many hours are in a day? 24. So 24 is T. Y subscript 0 is 10,000. And so then all I need to do is plug it into my formula. Y equals 10,000 times 2 raised to the 0.5 times 24. Okay, so that one, again, you'd now want to do that in your head. So let's grab our calculators and see. Let me get my other one. I think it shows up a little better than that one. So let me turn this one on. That shows up a lot better. So let me get out of my y equals. And so we're going to plug this thing in. So I'm going to put 10,000. Oops, one too many zeros. Times 2 raised to this. So I'm going to do a caret. Parenthesis 0.5 times 24 parenthesis. Now you want to do that and put it inside of parentheses, because that is an actual multiplication that's taking place as an exponent. So be real careful. Make sure you do that multiplication in there. And I'm going to get this thing back down. And if I hit enter, we're going to find that in that little Petri dish where there was 10,000 bacteria, after 24 hours, there are 4096000 with 4 zeros, is it? 1, 2, 3, 4. So my 10,000 bacteria now became 40,000 or 40,960,000 bacteria. All right. So they're a rapidly growing bacteria that is present at that point. So exponential growth, because as you look at this exponential piece in here, what is happening with this would end up giving us a graph that's coming across and doing one of those things to it, because the growth of that bacteria is increasing quite high. And we're starting out at 10,000. So what this means is the spot on my chart here is where my bacteria started at. Okay, so if I were going to graph this, I would start at whoops, I got that backwards, a y-intercept of 0, 10,000, and that's where I would start at, and then this rapidly shoots up here. So then this is out at 24 hours, and I have that number of bacteria. So that's what's taking place with these. So this point up here would be 40960, and it would be showing what's happening to that. Okay, so I get that growth, and I get that pattern going on in there. Okay, so that's one. So we worked it from where we were at back. This one is a little different because it's saying, okay, we have used the formula of exponential growth. So this one's changed a little. Notice these two are next to each other. Of course, we had the multiplication last time. So to determine the exponential function that fits the following information, y subscript 0 is 5,000, and there are 135,000 bacteria present after 3 days. And our growth is based on days. So we're going to plug in what we have. So 135,000, that's y. Then what we have is 5,000 times b to the third power. And we are trying to find out what b happens to be in this case. So to solve it, I need to divide both sides by 5,000. And so 135,000 divided by 5,000 is going to equal 27. And so I have 27 equals b to the third power. And so what is b? Well, we know from chapters 9 and 10 that we can take the cube root of each side and find out what that value would be. So my cube root is underneath math, number 4. Type in 27, get out of there, hit enter, and I find out that b is equal to 3. So we have a 3 is our exponential base. So our formula would be y equals y subscript 0, 3 to the t power. So we were locating what b happened to be in this case. So it's a little different because I knew what my value would equal. So that was on this side. Yes? What do you think? Okay, good. As long as we've got that stuff. And that's again with the bacteria. Then we have compounded interest. So if you went and put your money in the bank and your bank said we're compounding and we're getting our interest together here, we just used this in basic math the other day. So my basic math students, we were compounding interest in there. So what are all my pieces in here? So my A is my interest. My P is my principal. My 1 stays, the R is the rate. The N is the number of times it is compounded. And the N is also up here in my exponent, so that's also N, so that means the same thing. And then finally T is the time. So we're looking at how long we have put it in for. How long has it been in the system, or if I put it in for 3 years, did I put it in for 5 years? So my time is my other piece that's in there. All right, with those. So again, and your rate is in decimal form, so you need to turn it back to a decimal. So it's a percent, move it back 2 to the left, and the decimal point 2 to the left, and you'll have your percent or your decimal representation for your rate. Okay, so let's see what we can do with that formula and see what ends up happening to it. So it says if P dollars were invested at a rate of interest R, compounded annually once a year, N equals 1, T is T years, the formula for the amount of A, and they give you the formula. And it gets changed here because it's only for 1 year. Notice that if you put 1 here and 1 up here with my time, they basically cancel each other out. So you ended up changing it. Now, do you have to change it? No. You can still work with the same formula in there. And this says find the $1,000 invested at 6% for 3 years. So we have P is 1,000, my rate is 0.06, and my time is 3. So again, that stuff. And so then, oops, let me get it down here where we can see our formula. In fact, let me rewrite that formula. P times 1 plus R raised to the T power And now we can look at our pieces that we have. So if we plug our stuff in, and basically this whole section is doing nothing more than plugging in pieces. So I'm going to put 1,000 in my principal, 1 plus my rate, which is 0.06, raised to my time, which is 3, and solve it. So what would it end up working out to be? So 1,000 times parenthesis 1, and if you got parentheses in your formula, put them in your calculator. 0.06, close it, raised to the third power, and we find out our answer is 1191, and round to the nearest cent, so I'm going to have 0.02 cents. So that's what would be in the account after 1 year if you had 6% interest. Not hard. You guys following okay? So basically it's just figuring out where your numbers go and then sticking it, of course, on your calculator to calculate out what it would be. So we go to the next one. The next one is this one. And so my formula was A equals principal times 1 plus the rate over n raised to the n to t. And again, you will have these formulas. It's not like they will not give you the formula in the problem, okay? It will be there. If you take your test, your formulas will be there. So don't say, oh, I got to memorize all these formulas. They will be there for you, okay? So you'll have them to work with. So, and you might have to, in your homework, keep track of the 3 different ones that you're working with because it may not pop up if they give you another problem just like it for the one before. So, find my pieces. This is what will the value of the principal investment of $10,000 invested at 6% for 3 years if the interest is compounded monthly. So what is the difference here? And it says use the formula. So principal is 1,000. My rate is 6%. My number of times is going to be, it can be 1 if it's a year. If it's 12 months, it's 12 months. If it's a days, then it's 360 for days. You know, so if you run across one that asks for days in there. And then t equals 3. So plug them in. So you got 1,000 times 1 plus 0.06 all over 12. And 12 times 3 on the outside. And then we stick all that into our calculator and see what we end up with. So 1,000 times parenthesis 1 plus 0.06 divided by 12 parenthesis caret or exponent 12. Oops, backspace. I gotta put that inside of parentheses. Parentheses 12 times 3 parenthesis. Or you can just put 36 in there because 3 times 12 is 36. And get it back down and hit enter. And you get 1196 68 cents. So did we have much difference in our investment? I think the last one was 19602. So we gained not too much by compounding it monthly. Okay, but same process with that one. So there's a difference there with what we got going. Questions with this stuff? Pretty good so far, hey? Not hard. It just ends up being the value. This one, the only difference is 360. So if I pull back my, So if I pull back my problem, I can just simply go in here, change a couple things. I'm going to change my 12 to 360. And you want to go second insert to get your 0 in there. And then up above, we are going to change my n out here to 360. Times 3. And we can hit that and come up with our answer there. Made a little more. Not a whole lot, but it changed. So if you get a chance to have it compounded daily, you might make an extra $1. Not a whole lot. So it doesn't make that much of a big difference. Now, if you had large sums of money, it would end up making a big difference in what you had there. Okay, and then we got to talk about the letter E, or an exponent, that we have a base of E. E is the opposite of a natural log, and you have this on your calculator. If you look above your ln key, or your natural log key, there is an e to the x in there. So that's real important. So if you get any e's in any of your formulas, it's right here. So ln's right there, e to the x is right above it. And so all you would do is, if I wanted to know what that happened to be, and this number is in my calculator, so if I just put 1 in there and hit enter, that number that they give me right here is in my calculator. Okay, so it's right there. So we know what that happened to be. Years and years and years ago, we had tables that had all these in it, and you had to go back to your table and find out what it was equal to, then times it by what you had to multiply it by. So calculators are wonderful, handy-dandy things. But again, right above your ln key is where your e to the x happens to be with those. And so these next formulas are going to have that value in, because now we're looking at continuously compounded interest, and this e that's right here is the e that we will use on our calculator when we do this, raised to the RT. P is still principal, A is interest, P is principal, E is my exponent piece, and you get that by doing your natural log function. R is my rate, and T is the number of times, or the number of years that you happen to have in there. Okay, so let's see if we can do one of these guys and see what happens to it. So it says find the value of 1,000 invested at 6% for 3 years if the interest is compounded continuously. So we've got 1,000, 6%, which is 0.06, and time is t. So we plug it all in down here. We put our 1,000 in, our e, which we're going to use on our calculator, times this. And remember, this needs to be inside of parentheses when you do that. So put 1,000 on your calculator, or you can see, times second, the natural log. So it'll put an e on my calculator. And then I need to go parenthesis 0.06 times 3, parenthesis, get it back down, and hit enter. And it still didn't make that big of a difference. So our dollar amounts and our stuff that we've invested using this $1,000 hasn't changed very much throughout one to the other. Okay? All right, does that make sense? Hopefully. Okay. So now that gets us to the end of those. So let's go and see what we can do with your sheets that you happen to have that are in front of you there. Let me get my calculator up to the side over here. And let's see what we can come up with. So again, formulas will be in these. So we've got this one in here. So that's kind of similar to the first one we did. So what do we have? It says a scientist has 12,000 bacteria present when t equals 0, and she knows that the bacteria grows according to the function of y equals 0.3 raised to the 0.25 times t. Find the, when it's measured in hours, how long will the bacteria be present at the end of one day? So we got 24 hours. So y equals her beginning bacteria times 3 raised to the 0.25 times t, and t is 24. And you just simply plug it on your calculator and away you go. So you probably like a whole bunch of these on your test. That would probably be your best thing there. So put it in. Times 3 raised to the parenthesis 0.25 times 24. And we get an answer of 87400. Oops, 874,800. Okay. Lots of bacteria. Okay. And the next one happens with this guy. So it says determine the exponential function that fits the following. Starts out at 7,500 bacteria, and there were 12,000 bacteria present after 4 days. And we're using this formula. So 12,000. Y0 is 7,500 times B, which we don't know, raised to the 4th power. So let's see what we get. Divide by 7,500. And get 1.6 is equal to B to the 4th. Take the 4th root of each side. So that I need to go into my math, but in order to use it, I need to tell it 4 first. Then go to math, go down to your number 5, which puts the 4th root of 1.6. Hit enter, and B is 1.1247 if we round it to 4 decimal places. So that would be my solution to that one. Okay, think you're getting the hang of these? Okay, that's kind of what I thought. They're not really that bad to plug stuff in. Here we've got an interest rate. If P dollars is invested at a rate of interest R in decimal form, compounded annually for 1 year, the amount A becomes this. Find the value of 13,000 invested at 5% for 4 years. So again, it's just plugging stuff in. So A, principal is 13,000 times parenthesis 1 plus my rate, which is 0.05, times my T, which is 4. And again, I think you can solve that, right? What do you get? You guys solve it. Let's see what we come up with. So after 4 years, hopefully you got that. 15,000, is that what you came up with? It's just an exercise in putting your stuff in the right spots to come up with what your values would be. Okay. Oh, 801. No, we cheated him out of some money, didn't we? Yep, there is an 8 there. Looking at it, I was thinking it was a 0, but it's an 8. Yes. Okay. So backside, similar type problems. Similar type things that they're asking you to do. Now the top one changes. It gets out of compounded interest and also bacteria stuff, and we get into a new formula, but the process is still going to be the same, that we still end up using this is as the value V at the end of T years is given by this. When C is the original cost and R is the rate of depreciation. Find the value of a machine at the end of 2 years if the original cost is $527 and the rate is 0.21. So we just plug stuff in and round to the 2 decimal places. So V, C is the original cost, 1 minus the rate of depreciation, raised to the time T, which is 2. So again, it's the same process. It's just that you have a different type of a formula there to work with. And so still same process. So 527 times parenthesis 1 minus to 1, parenthesis, squared. And we get the new price is going to be $328.90. So that's its new value once we do that. Okay, not bad. Again, kind of like a business applications in here. This one, I think I got a missing parenthesis here somewhere. Must be at the tail end of it. So if we look at the next one, CT of a drug in the bloodstream after T minutes is given by this formula. What is the concentrate after 4 minutes? Round to 3 decimal places. So T is going to be replaced with 3. And so we're going to come up with what our value would end up being for this one. Pardon? T is replaced by 4. Yep, sorry I said 3 because 3 was down there, but it's 4. So we have 0.06 times 1 minus e to the negative 0.2 times 4. So let's see what we get. So 0.06 times parenthesis 1 minus e, second, the ln key to get it in there, parenthesis negative 2 times 4, parenthesis, whoops, parenthesis, I gotta go back here and get it down first. And I get 0.05, and we're to round to 3 decimal places. It's actually going to become 0.06. Pardon?
I think you put just regular minus 2 is 0.2.
Oh, okay. Let me bring it back up. Second, enter, and we will go back in and fix it. Second, insert 0.0. There we go. That'll fix it. Now we got something different. So, well, we'll get it right yet. Get rid of the 0. Now we got it right. Okay. After we get 60 answers up here, 0.033. There we go. Now we got it right. Okay. Yep. It helps if I get what I'm supposed to get in there with those. Okay. And then this one, again, uses the formula. So I don't know. Do we need to do more of those, or do you think you're okay? I know I put a lot of them in here. This one, again, is just plugging in your answers, plugging in your pieces, and making sure that you come up with what you're supposed to. Let's see what's on the back side here, and I'll fill these back in if we're missing them for the notes that get posted. This one says, what will the value of the principal of 13,000 be if you got this interest? Again, same type of problem, but there's an H in here, which is still meaning the base number of times that it's quoted. So 12 times would be the H piece that's in there. And then same thing here, and then the bottom one is the same. So I don't think we need to do those. You guys okay with that, you think? Okay, so as long as we, pardon? Daily is 360. Yep, like this one's 360. Yep. They don't calculate it with 365. Don't ask me why. I guess you got 5 free days that they don't give you any interest. But yeah, if it says daily, it's 360 in there, and that's what replaces H in this case with those. So you get some pretty big exponential values in there. But yep, okay. All right, and then they give some practice problems in here, but again, we're not doing the graphing piece. So you would not find, you'd have to find 3 points on your graph, and you could just simply put this into your graph. So if you go to y equals, and we're going to clear out what we got in here because we're done working with the stuff from the first, or from section 11.1, that we had that combination. But if you simply put in there 2 times 3 caret x, and you get a graph. So just so you know what your graph is going to come in looking like, again, it's showing that. If you need 3 points, all you do is go second to your table, and it will give you a lot of points. So you can just go through and pick points out of there. So I might pick 0, 1, and 2 because they're all good solid numbers in there. And so we have those. Now the reason, if you go up on here in your negative values are in here, they get to be decimals. That's because negatives make it move to the denominator. So it would say this is going to become 1, or become 3 in the denominator, which makes it all of the decimal values. So you would, in the first one, if you raise as the negative second power, you would have 3, or 1 over 3 to the second power, or 1/9. So 2 times 1/9, that's where we're getting all of our decimal pieces. So negative exponents become fractional, or become decimals in this case that we're working with. So that's why that happens. And then another one, and then they give you this one in there too. And here's the answers to those. So if you were looking at them, you would end up finding that you've got your 3 points and your 3 points, and then your 2 values that would calculate out with the story problems that are in there. Okay, so so that's that piece. Questions on any of this stuff? Pretty straightforward. Probably the easiest story problems we've had because they are just simply figuring out what your exponential values would be when you put them in there. Okay, so yes, I'm going to post the ones to the rest of them. I will work those out and get them in the notes for those, and so you'll have them that go in that spot. Okay, do we need a break? What do you guys think? Yes? Yes? Okay. Take 5. Okay, let's finish up 11.4. The other sheet I handed out, we'll talk about that in that single sheet. So the single sheet, I don't think. Here says Elizabeth. Oh, did you get those?
Oh, yeah.
Oh, okay. I couldn't remember if I gave them to you or. Oh, I did. That's right. I did. I got them to you at the beginning. Okay. 11.4 is doing some more stuff with logarithmic functions, and all logs are connected to exponents. They are another way of writing an exponential notation that we're working with. And so as we go through these, we're going to write exponential expressions in logarithmic form, write logarithmic expressions in exponential form. They're not hard. You just got to reverse a couple things around. You learn some basic properties and evaluate equations, and then we're going to graph. But again, we don't end up getting into graphing the stuff as much with this part as we did in others. So, definition of a logarithm. A logarithm in base b. B, remember, has to be larger than 0, and it can never equal 1, so that's going to hold true for everything. X is equal to by. This is exponential form. So b to the y power is equal to x. You could write it the opposite way as well. Is evaluated to be y equals log bx. So what this means is that if you have it in this format, x equals b to the y power, x is your answer, b is your base, and y is your exponent. Okay, so if we had something like 4 equals 2 to the second power, we're saying 4 is my answer, 2 is my base, and 2 is my exponent. If I want to turn that into logarithmic format, I still pay attention to what my letters are. Y is my exponent, log is log, b is the base, and that's a little subscript piece. So it's a little number that comes below log, and then your answer is what you have at the tail end. So if I wanted to turn this thing into logarithmic notation, I would say my exponent is 2, log, my base is 2, and my answer is 4, and I've turned it into logarithmic format. Okay, so not hard, just remembering where your pieces happen to be and where they happen to fall into place with. So then it's read, y is the logarithm base b of x. So the logarithm of x, in other words, is what we're looking at. Now, if they put them the opposite way, and we're going to go through and do a bunch of these so that you can get an idea of turning them around, you could also see this in that format too. Okay, so you could see it where your exponent piece is first equal to your answer, and I actually think they're a little easier to work with this way because you got your pieces, base, exponent, answer. These also are written in the opposite direction as well too. So they mean exactly the same thing. It's just another way of seeing those as you go through and take a look at them. So let's go through and do some. Let's see if we can get all of these turned into logs. We've got a bunch of them in here, so let's see what we can do with them. So in my log format, it's log, base, answer, equals exponent. So we'll put that in place and see if we can write this into logs. So we've got log, base is 2, answer is 8, is equal to 3 of the exponent. Okay? So it's that pattern. So what happens with this next one? So the next one is log 2, the answer is 16, the exponent is 4. So if you get that pattern down, we're going to bounce back and forth between these for the rest of the chapter. So we're going to switch stuff into exponential form because sometimes they're easier to solve that way than to solve them looking at them as a log. And so we've got ways in which we can work with that. So then this one will be log base of 10, answer of 10,000 or 1,000 is equal to 3. Okay. This one is log base of 3, answer of 1 is equal to 0. Okay. And finally, the last one is log 5, 1/5 is equal to a -1. Okay. Good or not good? So again, don't forget it's log base. Whatever the answer is from your exponent is going to equal the exponent. And we could say this has a base of 2 and a log of 3, a base of 2 and a log of 4. The last one, or the C, is a base of 10, a log of 3. Okay. And the bottom one is base 3, log of 0. And the last one, base 5, log, oops, -1. Okay. We good? Yes. We got lots more to practice with these things too, so we'll see. Then if we switch it back and we go from logs to exponential form, and a lot of times if we do this, it's going to help us come up with what an answer will be for our whole problem, because we're going to get into having x's in here and having things that we don't know of what they are. And if we put it back into exponential form, sometimes it helps. So if I go back into exponential form, you have base exponent equals answer. So base exponent equals 2. Base is here in my log. Exponent's over here. So this is base exponent. And the 2 is answer. So keep that in mind when you're doing these. So we're going to reverse them and bounce them from one to the other. So if I look at this one, 6 is my exponent, or my base, I should say. X is my exponent. It's equal to 216. And we're going to solve these and figure out what in the world does that equal. What would x equal once we get there? Here, what's the exponent 1 on that one? Let me get over here a little bit. It's a 9. 9 to the 1/2 is equal to 3. And if you remember back in chapter 9, we had these 1/2s and they met the square root. So the square root of 9 does equal 3. So I know I did that one correctly. And about this next one, what is it going to become as an exponent? So if I say put it back into exponential form, 4 base 2 is the exponent, and it equals 16. Now, if you look at these and you rewrite them and they don't work out to be what the answer is, 4 to the 2nd power is 16, you know you wrote something down wrong, okay? So you want to double check them and make sure they do make sense. Last one, 3 is my base. Exponent of 3 does equal 27. So 3 times 3 is 9, times 3 is 27. So we know we did that one correctly. You okay with that, or need to do more of them? Just pay attention to where your locations are at. Pay attention to what pieces are in there and what you have to do with that part. Okay, so a note is that in each case, the base of the exponent is the base of the logarithm. So the base meaning that little number in your logarithm. So if you have log base answer equals exponent, or you have base exponent equals answer, every one of these, you've got your base in there, okay? Your base is that value. So your base is right here with all of them, okay? All right, now the properties. You do not need to frantically write this down because that's on that sheet. I gave you this sheet that has these laws on it from 11.4. It's got what we've got going with our pieces up here. It has our laws that are in here, and these are the same ones that are in this on that sheet. So you've got this to hang on to. So you got that. So you don't have to write frantically on what those are. If you want to put little notes on that piece, you can, so that you have that part. In here, what do we have happening? So if I look at this piece, if my base here and I've got a 1, it's always going to be equal to 0. Because if I reverse this, b to the 0 power is equal to 1. So if you happen to see that, or if you don't see it, reverse it back into exponential form and you will see why it equals what it does. Okay, so log b 1. So another example of that one might be log 3 1 equals 0. So I've got a 3 in here. 3 to the 0 power does equal 1, and so it works out that way. The second one, you guys in the back. So the second one back here is we've got a base, and we've got b is equal to 1. So if these two match, it's always going to be equal to 1. So an example might be log 3 is going to equal 1. So if I see log 3, I know I'm going to get 1 out of it, if you can remember that. If you can't, reverse it and turn it back into exponential. B to the first power is going to equal b. So the 1 is what I'm looking for. So it's going to go back to the first power, and I will know that I'm going to have it be equal to 1. And this one's a little strange because it's got b raised to a log. But if you have b raised to a log with a b here, your answer is just simply x. So you end up with x, and x needs to be bigger than 0 if you use that one. And finally, in this last one, bx, it's going to end up equaling x if you see a match in there. So if you have log 4x, it's going to equal x. If you had log 5, 3, my answer is going to be 3, because these again match in there. Same as it does here, these match, so it's going to be x with that one. Okay? Again, these laws are here. They're laws that apply, but if you always bounce it back to an exponential form, you'll be good. So even if you can't remember these guys, you'll be good with that one, because you can end up coming up with what they happen to be. So let's, these are some examples of what we happen to have with these different properties. So this one, 3, 1, set it equal to x. If you set all of these equal to x, that's going to help you out, because now what do I have? I have 3 to the x power is equal to 1, so I know x must be 0, because that's the only thing that lets me get 1 out of it. Okay, so it has to be 0. Bottom one, 8x. So 8 to the x power is equal to 8. If I go back to exponential form, base, exponent, answer, what would I put on 8 that would give me 8? Just 1. So x equals 1. So you'll know it's 1. And then this one's kind of the weird, crazy looking thing. So whenever you see that, just remember that your answer is going to be whatever that number is on that one. And I don't know, it seems to be that I remember that we had pulled those out of your homework, but I can't remember for sure. But I think they're not in there. So it's going to be 20. And then these two, what will my answer be? Well, 32 can be broken down into 2s. It's 2 to the 5th power. So really I have log 2 to the 5th power. And so that's where they get the answer 5. If you don't know that, set it equal to x. 2 to the x power equals 32. What would I have to replace x with to get it to be equal to 32? And 32 breaks down to 2 to the 5th power. And we're going to find that these, if the bases match, we found that in our another chapter, if our bases matched, our exponents were equal. So x equals 5. So you can do it that way too. And finally, the last one. Again, if you can't remember the properties, set it equal to x. So 10 to the x power equals 0.01. Because it's a decimal, this becomes 10 to the negative 2nd power because it's 2 off. And so I find out that x is equal to a negative 2. Again, it's knowing what your bases happen to be and what you're coming up with for those. So if you can't remember them, I'm not going to test you and say, okay, property 1 is what? Property 6 is what? You don't have to do that. You just have to know how to work some of these things out. And we'll go through and get some more examples of what you got to do to work them out. Okay? This one, in solving them, one of the easiest ways to do that is to reverse it back into exponential form. So we're going to put it back into exponential form. So 16 to the 3/4 power is going to equal x. So once I get it back to that part, then I can just find it. So if I find it, just use your calculator. So 16 raised to the 3 divided by 4, or 0.75 if you want to put that in there. And you're going to get an answer of 8. So reverse them back to exponential, and usually you can figure out what the answer is going to be within these. So switch them around, get them back so that they end up matching, and you can come up with what the values would be. So all I did is base was 16, exponents out in front, it's the equals to x, which is the answer, and I got it to work out right. Okay, let's do this one. So we've got log 4, 8 equals x. And I got a few of these in here so that you get an idea of what you got to do with them. So put it back into exponential. 4 to the x is equal to 8. Now looking at that one, you're going to say, nothing matches. I can't work stuff out. But if I can get my exponents to match up here, I can solve it. 8 is 2 to the 3rd power. 2 times 2 times 2. We good there? 4 is 2 to the 2nd power raised to the x, or 2 to the 2x is equal to 2 to the 3rd power. We good or not good? These are a little tricky sometimes. If the bases match, set the exponents equal to each other. So 2x equals 3, divide by 2, and we find x is 3/2. So that's my solution. Now these are exact. This week on Wednesday, we're going to find out what they are in our calculators. So our calculator is going to do some of our work for us. But these are exact, so we want the exact answer with that one. And then this one is 8 to the x is equal to 2. If you reverse it. So what's x going to be? Two to the 1st power, 8 is 2 to the third. So 3x equals 1. Divide by 3. And we find x to be 1/3. And if you want to check it, you can, because now we can put 8 raised to the parenthesis 1 divided by 3. And it comes out to be 2. So we know we did it right. And the last one, see what you get. What happens with that one? So you should have found x equals 1/2 if we did it right. Okay. These aren't too bad. You just got to read carefully with what it's asking you to do when you get to your homework part with it so that you know what's taking place with those and so forth with that. We need to do more of these. What do you guys think? No? Think you're good? Okay. Examples of extra ones that they have in here, practice problems. Again, expresses logarithms. So if we express these, we're going to find that we have log 4/16 equals 2. This one, log 3 or log 5/125 equals 3. And the last one, log 10/1/10 equals -1. So they're pretty easy once you get the gist of what you're doing. So again, base, answer, exponent. Base, answer, exponent when you do logs. And if you go from a log back to exponent, it's 2 -1 equals x. So what would x be for an answer if we had to solve this one and finish it? So x would simply be 1/2, because you would reverse this and invert it. 5 to the second equals x. So 5 squared is 25. So that's x. 3 to the 0 power is equal to x, or x is equal to 1. So as you work through those, you can end up coming up with what their solution is with that. So be careful with those. These use your properties. 64, set them all equal to x. If you get lost using those properties, set them equal to x, because it'll tell you where you're going with it. Because now I have 2 to the x power equals 64. So 64 breaks down to 2 times 2 is 4, times 2 is 8, is 3, times 2 again is 16, times 2 is 32, times 2 is 64. So really, I have 2x equals 2 to the 6th power, so we know x is equal to 6 when you do that one. This one, 3 to the x, is equal to 27. So 27 is 3 times 3 times 3, or 3 to the 3rd power. So x equals 3. And finally, 7 to the x equals 7, so x must be 1. Okay, so that's the thing with this piece, is just be real careful with what they have. And again, these are the ones worked out, so they're a little bit spread out more than the other parts. Let me pull that down so we have it all in there. So if you're watching this, you can end up knowing what you got to do with those. And then finally, the full-fledged answers that are given for those. So, okay, all right. Any questions in doing this piece? Again, pretty straightforward. What you do have to do. And again, it plays a role with other stuff we're going to do. So it ties in with 11.7 when we get there. We'll do some more stuff with it. Okay, questions on any of that? Alrighty. This thing shut off.